Testing, can you hear me? Hello. Testing, can you hear me? Hello. Okay, so I'm going to be reading data structures and algorithms again. Hold on. Okay, so I'm going to be reading data structures and algorithm again. I'm going to be starting where I left off. So I studied about merge sort. So I was studying about the three sorting algorithms: insertion, bubble, and selection sort. And then after that, I learned about shell sort and then merge sort. Now I'm going to be reading the rest. Hold on. All right. So let's start with quicksort. While merge sort uses the most obvious form of divide and conquer, split the list in half, then sort the halves, this is not the only way that we can break down the sorting problems. We saw that doing the merge step for merge sort when using an array implementation is not so easy. So perhaps a different divide and conquer strategy might turn out to be more efficient. Quicksort is aptly named because when properly implemented, it is the fastest known general purpose in-memory sorting algorithm in the average case. It does not require the extra array needed by merge sort, so it is space efficient as well. Quicksort is widely used and is typically the algorithm implemented in a library sort routine such as Unix qsort function. Interestingly, Quicksort is hampered by exceedingly poor worst case performance, thus making it inappropriate for certain applications. Before we get to Quicksort, consider for a moment the practicality of using a binary tree for sorting. You can insert all of the values to be sorted in a BST one by one, then traverse the complete tree using an in order traverser. The output would form a sorted list. This approach has a number of drawbacks, including the extra space required by BST pointers and the amount of time required to insert nodes into the tree. However, this method introduces some interesting ideas. First, the root of the BST splits the list into two sublists. The left contains those in the list less than the root value, while the right contains those values in the list greater than or equal to the root value. Thus, because BST implicitly implements a divide conquer approach to sorting left and right subtrees, Quicksort implements the same concept in a much more efficient way. Quicksort first selects a value called the pivot. This is conceptually like the root node's value in the BST. Assume that the input array contains k records with key values less than the pivot. The records are then rearranged in such a way that the key values less than the pivot are placed in first or leftmost k positions in the array. The values greater than or equal to the pivot are placed in the last or rightmost n minus k positions. This is called a partition of the array. The values placed in a given partition need not be sorted with respect to each other. All that is required is that all values end up in the correct position. The pivot value itself is placed in position k. Quicksort then proceeds to sort the resulting subarrays now on either sides of the pivot, one of size k and the other of size n minus k minus 1. How are these values sorted? Because quicksort is such a good algorithm, using quicksort on the subarrays would be appropriate. Unlike some of the sorts that we have seen earlier in this chapter, quicksort might not seem very natural in that it is not an approach that a person is likely to use to sort real objects. But it should not be too surprising that a really efficient sort for huge numbers of abstract objects on a computer would be rather different from our experiences with sorting a relative few physical objects. Here is an implementation for quicksort. Parameters I and j define the left and right indices respectively for the subarrays being sorted. Initial call to quicksort would be quicksort array 0 and minus 1. So quicksort the array and then I and j. So pivot index, find pivot, pick a pivot, and then swap. Pick a pivot at end. K will be the first position in the right subarray. Partition swap. Okay, I don't understand this very well right now. Function partition will move records to the appropriate partition and then return k, first position in the right partition. Note that the pivot value is initially placed at the end of the array, position j. Thus, partition must not affect the value of array position j. After partitioning, the pivot value is placed in position k. Adjusts its correct position in the final sorted array. By doing so, we guarantee that at least one value will not be processed in the recursive calls to quicksort, even if a bad pivot is selected, yielding a completely empty partition to one side of the pivot. The larger partition will contain at most n-1 records. Selecting a pivot can be done in many ways. The simplest is to use the first key. However, if the input is sorted or reverse sorted, this will produce a poor partitioning with all values to one side of the pivot. It is better to pick a value at random, thereby reducing the chance of a bad input order affecting the sort. Unfortunately, using a random number generator is relatively expensive, and we can do Nini as well by selecting the middle position in the array. Here is a simple find pivot function. So find pivot, ij, return I plus j divided by 2. Highlight the pivot element for quicksort in the array displayed below. 6 divided by 2 is 3. Or what if it's odd number? 5 divided by 2 is 2.5, but I'm guessing it's integer division. Yep. Highlight the pivot element for quicksort in the array displayed below. The left pointer is at 0, the right pointer is at 11. So 11 divided by 2 is 5.5. So it will just be 5. 8 divided by 2 is 4. We now turn to function partition. If we knew in advance how many keys are less than the pivot, partition could simply copy records with the key values less than the pivot to the low end of the array and records with the larger keys to the high end. Because we do not know in advance how many keys are less than the pivot, we use clever algorithm that moves indices inwards from the ends of the subarray. Swapping values is necessary until the two indices meet. Here is an implementation for the partition step. while left is less than or equal to right. Move bounds inwards until they meet. So a left compared to pivot less than 0, left plus plus, and if right is more than left, and a right dot compared to pivot is more than or equal to 0, right minus minus. Swap out of place values. Return the first position in the right partition. Note the check that right is more than or equal to left in the second inner while loop. This ensures the right does not run off the low end of the partition in the case where the pivot is the least value in that partition. Yeah, I don't understand it very well right now, but I guess they will use examples. Pivot value 60 has been moved to the rightmost position. When we start the partition function, pivot value 60 has been moved to the rightmost position. The left and right bounds are set to positions 0 and 8 respectively. Now move left bound rightward as long as it is at a value less than 60. Since it starts on 76, which is greater than 60, then there is no movement of the left bound at this time. Likewise, the right bound starts at a value less than 60, so it does not move. Swap the values of the bounds. Now move the left bound to the right as long as it is the value less than the pivot. Less than the pivot, 6. Oh, now we reach 88. Now we move the right bound to the left until it reaches a value less than 60. Oh, so 42. Now the right bound is at 42, which is less than 60. Swap these two. Once again, move the left bound. Left bound is at 85, which is bigger than the pivot value. Move the right bound to the left until we reach a value smaller than 60. Step. Note that the right bound has crossed over the left bound, so the partition is done. Since the left bound has reached position 4, is the value returned by the partition function. So 485 will swap with 60. A, K, and J. Pivot element for quicksort is highlighted in the array below. Partition the array using quicksort. Wait. So this is the pivot element. So we start with the two ends, right? 0 and 8. Now move left bound rightward as long as it is a value less than 60. So this goes inwards as long as it's less than 655, but it's not less than 60, 655. 7, now it goes right as long as it's less than 65, so we end up with 30, right? Right bound starts at a value less than 60, so it does not move. Swap the values. This does not move. 30, however, will swap, right? The next one is 449. This one is 413. 449 is less than 655. Now, less than is fine. If we reach more than, that's an issue. From the right, if it's less than, then that's an issue. So these two swap. 258 and 413. We keep the pointer at 645, right? This will swap with 413. And then these two will swap at the end, right? Wrong. Step, step. So bigger, 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 smaller, and then swap it with the current pointer. Okay. Let's see. Let's try this again. Start with these two pointers. This is bigger, so we can step. Now this is smaller. Start with this. This is smaller. That's an issue. So this and this swap. Now we go in next pointer. This is smaller. That is an issue. Pointer this smaller. That is fine. Next pointer. This is bigger. That is an issue. We go next pointer. This is smaller. This swap. Hold on. Why? Smaller. From the left side, this is smaller. That is fine. From the right side, it's smaller. That is an issue. So these two swap, I guess. Hold on, I made a mistake. 8636454. This smaller, this is fine. 863 is over here. This is fine. You go next step. We reach 30. 499 is smaller. 656 is bigger. Now from this side to 85 is bigger. That is fine. 413 smaller. That is an issue. Oh, what will it swap with? Yeah. Okay. 774. So we start with this position in position 0. So 424 is smaller than 774. On the left side, it's fine. On the left side, it has to be smaller. So 443 is smaller. Wait. 443 is smaller. 952 is bigger. So on the left side, you cannot have bigger. So this 952 is an issue. Then on the right side, you cannot have smaller. So 318, this is an issue. So swap it with these two. Okay, now you go one left, 139, which is smaller, which is fine. 986, which is bigger, that is an issue. Swap it with 495 because 495 is smaller on the right. Now 422 is smaller and 80. What is it? All of them are smaller. So yes, this is fine. The partition function. Left is less than right. So you increment the left first, right? So 443. So start checking 716. This is bigger, that is fine. 393, this is smaller, that is an issue. This is a bit on the left side, we have a bigger number, that is a problem. So swap these two. So 368, that is smaller, that is fine. 668, that is bigger, that is an issue. So swap it. Oh, there's nothing to swap it with. 438. This is bigger than 288, that is an issue. So 100 being smaller is fine. 997 is an issue. We need to swap it. Let me go left. 231. This is smaller than 288, so we swap it with this 438. Now we go next 445. It's bigger than 288. This shouldn't be on the left side. So we swap it with 350167. So 982. This is bigger on the left side. That is an issue. We should swap it with. Oh, there are no more swaps. Are there any more swaps? No, right? 438. 100 is fine. 997 is not fine. So starting with 438. We start with the left one, right? Partition left is less than or equal to right. A left compared to pivot. So less than 0, left plus plus. Right has to be more than 0. So left is less than 288. So we increment left. And now the left pointer points at 1. 439 is more than 288, which is fine. So we increment. We are left with 231. And if right is more than the left, then swap the left and right. Yeah. No. Right is more than the left. Wait, hold on. For the left one, we keep incrementing until we find something that is less than 288. So from 0, we keep incrementing until we find which is less than 88. And it's index 1. So left points at 1. From the right, we keep incrementing. Wait. No, I got it reversed. From the left, the values have to be left compared to pivot. So as long as the value is less than 288, keep incrementing. Okay. If the value is less than 288, keep incrementing. So 100 is less than 288, increment, and then we end up with 997 at position 1. So left points at position 1, and then we go out of the while loop. Now same thing for the right. For the right side, it's flipped. If it's for the right side, as long as it's more than 288, we keep decrementing. So for 38 is more than 288, we decrement and then we reach position 8. 231 is less than 288, so right pointer stays at position 8. Now, if right is more than left, so they mean the pointer, right? 8 is more than 1, then swap left and right. Starting again from 235, so then we go 445. This is greater, this is greater, this is greater, this is smaller. And swap these two. Now 9 to 8 is greater. Then that's it, right? Here is a visualization illustrating the running time analysis of the partition function. Pivot is 4, the left, pivot right. Function partition contains an outer loop with 2 nested. So do they put the pivot at the end? Swap A in pivot index. Stick pivot at end. K will be the first. Okay, so they put the pivot at the end for some reason. And then they put the pivot back. Start what they do. Quick sort the left partition. And then sort the right partition. And what does partition return? It returns where the left and right meet, right? So if they meet here, 85 is returned. Okay, so 4 is it's the index that is returned, right? Let's swap the index k and index j. Okay, so swap 85 with 60. And then what? If k minus 1 is more than 1, quicksort ai k minus 1. So we take k minus 1. So 60 goes to the right position, right? All the four values here are less than 60. Five values here are more than 60. 60 ends up in the right position, and then we do quick sort with these four and then quick sort with these. Okay, and now I understand. So we shift it to the right, pivot to the right. Maximum number of times swap can be executed is s minus 1 divided by 2. In this case, left and right will move at most s minus 1 steps for each for a total of s minus 1 steps. K is 9 of any k. We first analyze the find pivot and partition function when operating on a subarray of length k. So two nested loops guarantees the movement left and right at least one step each. The maximum number of swap can be executed is s minus 1 divided by 2. In this case, left and right will move at most s minus 1 steps each for a total of s minus 1 steps. The first inner loop will be executed at most s minus 1 times, in which case left will end up at the pivot, the outer while loop will end. Second inner loop, while the second inner while loop can be executed at most s minus 1 times, in which case right will end at array position -1, the outer while loop will end. According to the outer while loop along with its two inner loop, accordingly, the outer while loop along with its two inner loop will move left and right a total of s minus 1 steps. Thus, the running time of partition function is theta s, where s is the size of the subarray. This is subarray of length k. They forgot k and wrote s. Left is less than right, while left is less than right. So 1, 2, 3, 4, 5, 6, 7. Maximum number of swap can be executed is s minus 1 divided by 2. There'll be s minus 1 counts, right? But we need to count the swaps as well. Second inner loop, the second inner while loop can be executed at most s minus 1 times, in which case right up at array position -1 and the outer loop will end. Quick sort, put 4, 3, 5 at the end, and then sort everything. So 928 is bigger, that's fine. 97 is smaller, that's fine. 25 is smaller, that's fine. 716 is bigger, that's not fine. So swap it with 195, which is smaller. Then move the right pointer and then swap. Now move the left, this is bigger, move the right, swap. And now move the left, end up in the same position, swap it with position 7. Okay. So this here is sorted. And now this array. Okay. So 25 and 97 is sorted. Wait, hold on. 97 is bigger. So we move the right downwards until we find something smaller in the right hand side. Okay. Right, this is done. Now we wait what move the pivot, select the pivot, move the pivot to the end, swap these two, And then, of course, move the pivot back. And now for the right side, put 982 here. This is smaller, this is smaller, and then that's it. Move the right bound to the left until it crosses the left bound or finds a value less than the pivot. Bounds have crossed. When the right bound crosses the left bound, all elements to the left bound, all elements to the left of the left bound are less than the pivot, and all elements to the right are greater than or equal to the pivot. As far as we go. If the length is just 2, we just like do an if then case to sort them, right? No need to do a quick sort for this thing. There should be an edge case for size 2. The visualization explains the worst case running time of quick sort. How many sorts? Heap sort, bin sort, radix sort. In pivot, n minus 3 amount of work. The worst case running time of quick sort is theta n square. But why n minus 1? When there are no records in one partition and n minus 1 records in the other. Okay, yeah, that's the worst case. You're doing all the swaps, right? Okay, okay. This is terrible, no better than bubble sort. When will this worst case occur? Only when the pivot yields a bad partitioning of the array. The pivot values are selected at random. This is extremely unlikely to happen. When selecting the middle position of the current subarray, it is unlikely to happen. It does not take many good partitions for quicksort to work fairly well. This visualization explains the best case running time for quicksort. What breaks the array into two equal halves. A pivot, A pivot. So the worst case is when the pivot is over here. The best case is when the pivot is over in the middle. N divided by 8 all the way till. So each arrangement will take theta n time, right? Theta n swaps. Theta n swaps, and then we do this again, theta n. This happens log n amount of time. So theta n log n work. Quicksort finds perfect pivot. Quicksort average case behavior falls somewhere between the extremes of worst and best case. Average case analysis considers the cost for all possible arrangements of input, summing the cost and dividing the number of cases. We make one reasonable simplifying assumption. At each partition step, the pivot is equally likely to end in any position in the sorted array. In other words, the pivot is equally likely to break an array into partitions of sizes 0 and n minus 1, or 1 and n minus 2, and so on. Given this assumption, the average case cost is computed from the following equation. Tk plus Tn minus 1 minus k T0 T1 C. Quicksort is a recursive function. Accordingly, we shall end up with a recursive relation to describe its average case running time. Average case cost is computed from the following equation. Hold on. So we start at random k, any position k from 0 to n minus 1, and it divides into k and n minus 1 minus k. If the pivot ends in position 0, the total running time will be Cn plus T0 plus Tn minus 1. A Cn here stands for the cost of the partition step. The pivot ends in position 1. The total running time will be Cn plus T1 plus Tn minus 2. Tn plus T2 plus Tn minus 3. N minus 4. We will make one reasonable. Oh, and then, okay, we add all of them and divide the total by n. We make one reasonable simplifying assumption. At each partition step, the pivot is equally likely to end up in any position in the array. Since we have n positions, therefore the average cost of recursive calls can be modeled as 1 over n. But where did the Cn go? Shouldn't Cn be counted in here as well? But we also need to add the cost of partition and find pivot functions, which is Cn for some constant c. By solving this recurrence, we'll have that quicksort's average running time is theta n log n. This is an unusual case that the average case cost and the worst case cost have asymptotically different growth rates. Consider what average case actually means. We compute an average cost for inputs of size n by summing up for every possible input of size n. The product of running time cost, the cost of that input times the probability that input will occur. To simplify things, we assume that every permutation is equally likely to occur. Thus, finding an average means summing up the cost for every permutation dividing by the number of permutations, which is n factorial. We know that some of these n factorial inputs cost O n squared, but the sum of all the permutation cost has to be n factorial O n log n, giving extremely high cost of the worst inputs. There must be a very few of them. In fact, there cannot be a constant fraction of inputs with cost O n squared. If even say 1% of the inputs have cost O n squared, this would lead to an average cost of O n squared. Thus, as n grows, the fraction of inputs with high cost must be going toward a limit of 0. We can conclude that quicksort will run fast if we can avoid these very few byte input permutation. This is why picking a good pivot is so important. What is the best case cost for quicksort to sort an array of n elements? Theta n log n. In selecting a pivot value, a simple thing to do is to always pick from the same place in the partition. We use this approach, doesn't matter whether we always pick from the first position in the partition, the last position, or the middle position. It's much better to pick the middle. The order of the input records has what impact on the number of comparisons required by quicksort? None. Constant difference. There's a big difference. The asymptotic running time can change. The order of the input records. Okay, yeah, I believe that. In which case, are the time complexity is the same for quicksort. Best and average only. Quicksort is a stable sorting algorithm. Go left, right. Eh, that's false, right? Yeah, yeah. It takes a given computer 1 second on average to run quicksort on an array of 1000 records. How long will it take to run quicksort on 1 million records? 1 second, an array of 1000 records. So it's n log n, right? So the relative growth, and you know this from the statement that the machine can do 10,000 comparisons per second. To get the answer, you first need to compute how many total comparison 1 million records will require. Average case running time is theta n log n. That's what I was thinking, but do I just input n? If I input 1000 to n log n, 1000 log, let's say base 10, 1000, 1000, get 3000. Can do 3000 stuff in 1 second. What about 1 million? Let me see. 1, 2, 3. And then 1, 2, 3. Hold on. Okay, divided by, okay, wait. We need to be 2000. Yes. Okay, so what I did was, I don't know why it does this. So the case is n log n. I inputted 1000. 1, 2, 3 log, and I did base 10. 2, 3, and I got this here is 3, so I got 3000. So 3000 stuff, 3000 computes in 1 second. So if I do 1 million, 1, 2, 3, 1, 2, 3, 2, 3, 1, 2, 3. I got 6, 1, 2, 3, 1, 2, 3. So if it takes these many in 1 second, this will take, so I divide this by 3000, I'll get 2000 seconds. Yeah, that's how I got 2000 over there. How many comparisons? 3000. Sort 1000 records to the nearest 100. Would it be divided by 2? N log n. It is n log n, yeah. 10 times 1000. This means about 10 times 1000 comparisons are required. Shouldn't it be log 10,000? I don't understand. I don't understand this. How many comparisons does quicksort require to sort 1000 record to the nearest 1000 comparisons? Maybe it meant 1000 over here. Wait. Yeah, I don't understand. Worst case is n square. Where is the pivot? The last position. Okay, I'll just go to the next chapter. Our discussion of heap sort began by considering the practicality of using BST for sorting. BST requires more space than other sorting methods and will be slower than quicksort or mergesort due to the relative expense of inserting values into the tree. There is a possibility that the BST might be unbalanced, leading to theta n square worst case running time. Subtree balance in BST is closely related to quicksort's partition step. Quicksort's pivot serves roughly the same purpose as BST root value, in that the left partition stores values less than the pivot, while the right stores values greater than or equal to the pivot. A good sorting algorithm can be devised based on a tree structure more suited to the purpose. In particular, we would like the tree to be balanced, space efficient, and fast. The algorithm should take advantage of the fact that sorting is a special purpose application in that all the values to be sorted are available at the start. This means that we do not necessarily need to insert one value at a time into the tree structure. Heap sort is based on a heap data structure. We didn't study the heap data structure, right? I think they do that. Or did we? We studied tree, but I don't, or maybe we did. This chapter 7, yeah, we did. Or the Marx heap. A heap is defined by two properties. First, it is a complete binary tree. So heaps are nearly always implemented using the array representation for complete binary trees. Second, the values stored in a heap are partially ordered. This means that there is a relationship between the value stored at any node and the values of its children. Oh yeah, the max heap and the min heap, I remember. Heap sorts has all the advantages just listed. The complete binary tree is balanced, its array representation is space efficient, and we can load all the values into the tree at once. Taking advantage of the efficient build heap function, the asymptotic performance of heap sort when all the records have unique key values is theta n log n in the best, average, and worst case. It is not as fast as quicksort in the average case by a constant factor, but heap sort has special properties that will make it particularly useful for external sorting algorithms. Okay, this is like operating system stuff. Initially, we start with our unsorted array. So 0, 1, 2, 3, 4, 5, 6. And we are supposed to imagine it as a heap sort. First step is to heapify the array. We use max heap. It seems counterintuitive at first, but you should see a why soon. Done heapifying. Okay. 88, 85, 83, 72, 73, 6, 48, 60, 42, 50 some. So we start at the end of the array, 85, and we go 9 minus 1 divided by 2, 4, which is 60. If it's 2, then it's 2 times 2 plus 1 and plus 2. Those are the children. Okay, so 9 minus 1. Since this is the first child, we will do minus 1. And then divided by 2, we have 60. And then since 85 is bigger, we swap 85. And then next 48. 48 is smaller, so it stays there. 72 is smaller, so it stays there. 88 compares with, well, it's 85. So, but 88 is bigger, so 88 will come here. 85 will stay there. 88 will be here, 6 will be here. And then we have 85, 48, 72. We did not count 83. 83, come check with its parent. 83 is bigger, so swap. 83 swaps with 57. Right? 42, this. Yeah, and then 83 is bigger than 73. So 83 swaps with 73. 73 ends up here. 83 ends up here. And lastly, it's 88. 88 checks with 83. And then a swap would occur. Let's see. Oh, whoops, it's 85 actually. Wait. 73. $85, 60, 85 goes up. 85 swaps with 60. 85 over here. 48 stays there. 72 stays there. 88. Since 88 is bigger than 6, 6 keeps going down, right? Yeah, we have to push 6 down all the way till here. Yeah, okay. Now we will delete the max element, which actually moves to the end of the current heap. Max element, so 88 and 60, they swap. Oh, so last and first and last swap position, and then the last gets deleted. Decrement, reheapify. Now ready to process. Delete this, reheapify. I mean, when we are doing the runtime analysis, like at what position are we starting? Are we starting when it's already heapified? Don't you have to count the analysis of the heapify function itself? 73, 42. Yeah, I understand what it does. Heap sort, max heap h. This is the heapify function, right? Remove max. Remove maximum exercise. Perform one iteration of heap sort. Swap the last key, the largest key, and restore the heap in the array tree shown below. Use the decrement button to reduce the size of the heap. So 91 swaps with this, and then decrement. And then we need to, so it's looking at the left and then seeing that, so it's looking at the children of 30 and seeing that 75 is bigger, so it swaps. And then looking at the children of 30 again, seeing that 31 is bigger, so it swaps. And then that's it. Now again, we do decrement 75, 11. Oh, we are supposed to do one iteration. Now 98, 44, decrement. Now 44, 94. 44, check it with the children, 93 and 92. 93 is bigger. And then 63 is bigger. 89, 14, swap. 82 is bigger. 68 is bigger. 23 is bigger. Oh yeah, and decrement. Sorry. Do they check which step is done first? So 8. Decrement and then copy this, copy this, copy this. What? Perform one iteration of the heap sort. Swap the last key, the largest key, and restore the heap in the array tree shown below. Use the decrement button to reduce the size of the heap. 89 and 14 swap, decrement. So is it the largest parent that goes up? So checking the 2 child, the largest that goes up. Checking the 2 child, it's the largest that goes up. Oh, I forgot that. 91, 45, decrement. So checking the children of 45, 53 goes up. 83, 12, decrement, 56, 51. This visualization presents the running time analysis of heap sort. First step in heap sort is to heapify the array. This will cost theta n running time for an array size of n. After swapping, the heap size is reduced by 1. The max heap property may be violated. Accordingly, the array should be reheapified. Shift, shift, shift. So log I amount of work, where I is the index of the current position in the heap. Since this process is done till the heap is empty, the amount of work can be modeled by the following summation. Since most of the heap nodes are located toward the bottom of the heap, distance from the root to the current last position in the heap will be, in most cases, log n. This summation is bounded by n log n. N plus n log n. Right. All key values were equal. The heap sort would cost theta n in the best case, because every call to remove max would result in calls to shift down that complete in constant time, because the new root value never swaps with this children. Building the heap is relatively cheap, requiring theta in time. Removing the maximum valued record from the heap requires theta log n time in the worst case. Thus, if we wish to find k records with the largest key values in an array, we can do so in theta n plus k log n. K records with the largest key values in the array. K small is a substantial improvement over the time required to find the K largest value records using one of the other sorting methods described earlier. Uh, all of them, right? Best and average? Nope, worse than average. Heap sort is a stable. Uh, I guess true. I don't know about the. Okay, no. So worst and average. The order of the input records has what impact on the number of comparisons required by the heap sort? Big difference, constant factor difference. That was a guess. I'm guessing most some of the answers. It is not stable. In which cases are the time complexity is the same for heap sort? Oh, this is the same question. Imagine that for the past year, you're paid as you paid your various bids, you then simplify a pile of paperwork into a corner somewhere. Now the year has ended and you have decided that it is time to sort all of these paper by what the bill was for. Indeed, pretty natural approach is to make some space on the floor and as you go through piles of paper, put the phone bills into one pile, the electric bills into another pile, and so on. Once this initial assignment of bills to pile is done, you can then sort each pile by date relatively quickly. Because each pile is fairly small, this is the basic idea behind a bin sort. Let's start with an especially easy situation. Consider the following record fragment to sort a permutation of the numbers 0 through n minus 1. Here is a simple bin sort on the permutation of the value 0 to n minus 1. Move each value ai to the position bai. So oh, so this, okay, done. But this only works if they're integers, right? Or if there's a numerical representation for them. Here is the key value used to determine position for a record in the finite sorted array. This is the most basic example of a bin sort where the key values are used to assign records to bins. This algorithm is extremely efficient, taking theta in time regardless of the initial ordering of the keys. This is far better than the performance of any sorting algorithm that we have seen so far. The problem is that this algorithm has limited use because it only works for a permutation of the numbers from 0 to n minus 1. You can extend this simple version of the bin sort algorithm to be more useful because bin sort must perform direct computation of the key value as opposed to asking which of two records comes first as our previous sorting algorithms did, and assume that the records use an integer key type. The simplest extension is to allow for duplicate values among the keys. This can be done by turning array slots into arbitrary length bins by turning array B into an array of linked list. This way, all records with key value I can be placed in bin bi. Second extension allows for a key range greater than n. For example, a set of n records might have keys in the range n plus n to 2n. The only requirement is that each possible key value have a corresponding bin in B. We assume that we know that the range of possible keys is 0 and a max key value. Here is an extended bin algorithm. So B linked list max key value plus 1. 0 max key value I plus plus. Let me see what they're doing. This time the input has values in the range 0 to 14. Move each value ai to position bai. 0 to 14. 0 to, yeah, I get the point. Total work required, that's it. Total work required is simply that needed to place each record into the appropriate bin and then take all the records out of the bin. Thus, you need to process each record twice for theta in work. Does this cost analysis really make sense? Actually, the last statement is wrong because it neglects a crucial observation. Yeah, what if it's like the largest value is 1 million? Taking all of the records out of the bins requires bin sort to look at every bin to see if it contains a record. Why not have an array storing two values? One is the value itself and another value which is the pointer to the next value. Thus, an algorithm must process max key value bins regardless of how many of them actually hold records. If max key value is small compared to n, then this is not a great expense. Suppose max key value is n square. In this case, the total amount of work will be theta n plus n square, which is theta n square. This results in a poor sorting algorithm. The algorithm becomes even worse as the disparity between n and a max key value increases. In addition, a large key range requires an acceptably large array B. Thus, even extended bin sort is useful only for a limited key range. Further generalization of bin sort would yield a bucket sort. Here, each bin, now called a bucket, is associated with not just one key but rather a range of key values. A bucket sort assigns records to buckets and then relies on some other sorting technique to sort records within each bucket. A hop is a relatively inexpensive bucketing process will put only a small number of records into each bucket. That a cleanup sort to each bucket will be relatively cheap. This is similar in spirit to radix sort. Okay, I think this is the last sort. Major problem with bin sort is that it does not work so well for large key values. Fortunately, there is a way to keep the number of bins small and the related processing relatively cheap while still using the idea of binning records that have similar key values. Consider a sequence of record with keys in the range 0 to 99. If you have 10 bins available, we can assign the records to bins by taking their key value modulo 10. Thus, every key will be assigned to the bin matching the rightmost decimal digit. You can then take these records from the bins in order and reassign them to the bins on their basis on the basis of their leftmost digit. We will define values in the range 0 to 9 to have the leftmost digit of 0. In other words, assign the ith record from array A to the bin using the formula AI divided by 10. They run array size 8, digits 2. 2 digits. So 0, 7, 1, 4, 5, 0, 9, 1. So 0 goes into 0, 7 goes into 7, 1 goes to 1, 4 goes to 4. Also, it's a linked list. Linked list. Yeah, keep going. Keep going. Now that we are done, don't we have to do this again? So this time it's the second digit, right? So 0. Now we are going in reverse. So for 22 goes in here and then 0 goes in here. And then 4 goes in here, 3 goes in here. Then 4 goes in here. Okay. 20. Wait, what? 100? Shouldn't it be this? Oh no, this is the last step. So everything in order. and the relative ordering stays the same. We have r is equal to 10 bins and the key values in the range 0 to r square minus 1. The total computation is theta n because we look at each record and each bin a constant number of times. This is a great improvement over the simple bin sort where the number of bins must be as large as the key range. Note that the example uses r is equal to 10 so as to make the bin computation easy to visualize. Records will be placed into bins based on the value of the first, the right of first the rightmost and then the leftmost decimal digit. Any number of bins would have worked if we interpret the key values in terms of the corresponding base. This is an example of a radix sort, so called because the bin computation are based on radix or the base of the key values. Move each record in the array to the appropriate bin based on the middle digit. 796. So 9 is the middle digit. 4 is the middle digit. 8 is the middle digit. 3 is the middle digit. 9 is the middle digit. 9 is the middle digit. 9 is the middle digit. As with mod sort, an efficient implementation of radix sort is somewhat difficult to achieve. In particular, we would prefer to sort an array of values and avoid processing linked lists. If we knew how many values would be in each bin, then an auxiliary array of size r can be used to define these lengths. Guide us to where each one starts in the output array. For example, if during the first pass the 0 bin will receive 3 records and the 1 bin will receive 5, then we could simply reserve the first 3 array positions for the 0 bin and the next 5 for 1 bin. Exactly, this approach is taken by the following implementation. At the end of each pass, the records are copied back to the original array. Radix, k-digit, initialize counts. Okay, this algorithm is confusing. This is in array, right? Array-based radix sort. We would prefer to sort an array of values and avoid processing linked list. We knew how many values would be in each bin. There's an auxiliary array of size r can be used to define these lengths. Guide us where each one starts in the input array. For example, if during the first pass the 0 bin will receive 3 records, I see the first 3 will be reserved for that 0 bin. I see. So the auxiliary array is over here. Starting radix sort, we process the digits from right to left. The first step will be to count the occurrences of digits from the input array. Okay. So with the last digit, it's 7, 4, 8. And but when we are doing it the second time, don't we need another auxiliary array? Wait, what's happening? So 7 appears one time, so increment that, 4, increment 4, increment 8, increment 7, 5, 1, 5, and then 4. Now we do a rolling summation of the count array to be used next as position. So 9, 8, count 9 is equal to 8 minus 0. I don't understand what they mean. Oh, the array size was 8. 8 minus 7. Oh, I see. How much is it taking up? How much space it takes up? Is that it? 3, 3, 1, 1, 1. So if it ends in 2, there's no 0 at the end, there's no 1 at the end. If it ends in 2, hold on, let me see. Now use the count array to decide where to move values in the auxiliary array. So 47 has a current digit 7, and then it goes to position 5, and then 4 goes to position 1, 8 goes to position 9. Sorry, 8 goes to position 7. Oh, I see. And then we increment it as well. 16, 7, 41. Why do we increment it though? Done with pass. And then move it back to the input array. 1. And then now we do the same with the second digit. 8. Size is 8, so 8 minus 0. 8 minus 0. 8 minus 1. 7 minus 0. Minus 0. 7 minus 4. 3 minus 0. 3 minus 1. 2. 2 minus 2 is 0. What if you ended up with a negative number? Radix sort analysis. Radix sort starts with an input array of n keys with k digits. Here we have n is equal to 12, k is equal to 2. The outer loop will be executed k times, 1 pass for each digit of key values. The second inner loop counts the number of keys to be inserted in each bin. This requires a single pass over input array. The third inner loop sets the values in the array input array to their proper indices within the output array. This requires a single pass over the count array that takes R units of work. Last inner loop simply copies the keys from the output array back to the input array to be ready to be processed. To be ready for the next pass of the outer loop, this requires n units of work. So wouldn't it be kn, where k is the number of digits? Since we have k is equal to 2, the outer loop will be executed once more. At the end, since the outer loop is executed k times and some of the inner loops are executed n times while others are executed r times, the total amount of work required is theta nk plus rk. Nk rk, okay. Because r is the size of the base, it might be rather small and can be treated as a constant. Thus, the total amount of work will be theta nk. Is it really a reasonable assumption to treat k as a constant, or is there some relationship between k and n? If the key range is limited and duplicate k values are common, there might be no relationship between k and n. To make this distinction more clear, use n to denote the number of distinct key values used by the n records. Thus, capital N is less than or equal to n because it takes the minimum of log Rn base R digits to represent n distinct key values. We know that k is more than or equal to log R capital N. Now consider the situation in which no keys are duplicated. If there are n unique keys, then n is equal to capital N. It would require n distinct values to represent them. So now it takes a minimum of log R n base R digits to represent the n distinct key values. This means that k is more than or equal to log Rn because it requires at least log n digits to distinguish between n distinct keys within a constant factor, meaning the number of digits is sigma log n. K is in, I keep saying sigma, omega log n. K is in omega log n. This means radix sort requires omega n log n time to process n distinct key values. Of course, the key range could be much bigger than log Rn bits. Of course, the key range could be much bigger. Log Rn bits is merely the best case possible for n distinct values. Thus, the log Rn estimate for k could be overly optimistic. The bottom line of this analysis is that for a general case of n distinct key values, radix sort is at best a omega n log n sorting algorithm. Okay, this part is confusing. I need to read another book for this. What is alphabet tree data structure? A tree data structure. What is this? Tree data structure for storing variable length strings. Level I of the tree corresponds to the letter in position I of the string. The root will have potential branches on each initial letter of the string. Thus, all strings starting with A will be stored in the A branch of the tree. Second language, such strings will be separated by branching on the second letter. Okay. Next chapter. An empirical comparison. Empirical comparisons of sorting algorithm run on a 3.5 GHz Intel. So 4 CPU. All times are shown in milliseconds. What is this up and down? So 10, 100, 1K, 10K, 100K. And then 1 million. So bubble sort takes the longest amount of time. Shell is this much quick with optimization. What is 4 over here? We have heap, quick, and merge. Quick took 143 milliseconds. That is really fast. Over here, it's not making any difference. Table 8.15.1 shows timing results for the action implementation of sorting algorithms presented in this chapter. The algorithms compared include insertion, bubble, selection, shell sort, quick sort, merge sort, heap sort, and radix sort. Shell. The difference between even though shell uses insertion, the difference is so huge. Finite two columns of each table show the performance for the algorithms on inputs of size 10,000 where the numbers are in ascending, sorted, and descending reverse sorted order respectively. These columns demonstrate the best case performance of some algorithms and worst case performance of others. So up. Okay, insertion sort is not going to make any difference. This is for 10K, right? This is for what? 10,000. Bubble sort is bad. Selection. So insertion got its best case. If it's descending, then quick sort still wins. Actually, no. Quick sort with optimization wins. This is 10K. Shouldn't like the worst case be worse than this, than the 10K one? Best case for some, worst case performance for others. Input size of 10,000. But I don't understand why it's down smaller than some of the cases over here. The O and square sorts are quite poor performers for large arrays. Overall, radix sort is a surprisingly poor performer. If the code had been tuned a bit shifting of the key values, it would improve substantially. But this would seriously limit the range of record types that the sort could support. Radix. I mean, it's not that bad compared to these three. Which of the following sorting methods will be best if the number of sorts done is the only measure of efficiency? I don't know actually. Quicksort maybe? Nope. Merge? No. Selection? Yep. When the merge sort merges two sorted lists of size m and m into the sorted list of size m plus n, it requires how many comparisons? It need to compare both m and n, right? So m, isn't it this? Or this? Wait. This, right? Wait. N, N, show me hint. Two records, select the smaller. Two sorted lists of sizes m and m. It requires how many comparisons? But I don't understand. Each record gets selected once. Each selection requires a comparison. Except for the last record. Okay, yeah. Which of the following sort is not stable? Merge sort, insertion sort, quick sort. Might use which sorting algorithm? Insertion. Which of the following sorting algorithms has the worst case complexity? Theta n log n. This, right? It's the same question. By now, you may have analysis for algorithms. These analyses generally define the upper and lower bound for algorithms in their worst and average case. For most algorithms that you know, analysis has been easy. This module considers a more difficult task, Analysis for the cost of a problem as opposed to an algorithm. The upper bound for a problem can be defined as the asymptotic cost for the fastest known algorithm. The lower bound defines the best possible cost for any algorithm that solves the problem, including algorithms not yet invented. Once the upper and lower bounds for the problem meet, we know that no future algorithm can possibly be more efficient. A simple estimate for a problem's lower bound can be obtained by measuring the size of the input that must be read in the output that must be written. Certainly, no algorithm can be more efficient than the problem's I/O time. From this, we see that the sorting problem cannot be solved by any algorithm in less than sigma n time, as it takes at least sigma n to read and write the n values to be sorted. Alternatively, I keep saying sigma, it's omega. Any sorting algorithm must at least look at every input value to recognize whether the input values are in sorted order. Based on our current knowledge of sorting algorithms, the size of the input, we know that the problem of sorting is bounded by omega n and O in log n. Computer scientists have spent much time devising efficient general purpose sorting algorithms, but no one has ever found that is faster than O in log n in the worst and average case. Should we keep searching for a faster sorting algorithm, or can we prove that there is no faster sorting algorithm by finding a tighter lower bound? This section presents one of the most important and most useful proofs in computer science. No sorting algorithm based on key comparisons can be possibly faster than omega n log n in the worst case. This proof is important for three reasons. First, knowing that widely used sorting algorithms are asymptotically optimal is reassuring. In particular, it means you need not bang your head against a wall searching for in sorting algorithm, or at least not one that is in any way based on the comparisons. But it is hard to imagine how to sort without any comparisons. Even radix sort is what? Even radix sort does comparisons, though in a quite different way. Second, this proof is one of the few non-trivial lower bound proof that we have for any problem. That is, this proof provides one of the relatively few instances where our lower bound is tighter than simply measuring the size of the input and output. As such, it provides a useful model for proving lower bounds on other problems. Finally, knowing a lower bound for sorting gives us a lower bound in turn for other problems whose solution could be made to work as the basis for a sorting algorithm. Process of deriving asymptotic bounds for one problem from the asymptotic bounds of another is called a reduction. Except for radix and bensol, all of the sorting algorithms we have studied make decisions based on the direct comparisons of the two key values. For example, insertion sort sequentially compares the value to be inserted into the sorted list until a comparison against the key value in the list fails. In contrast, radix sort has no direct comparison of key values. All decisions are based on the value of specific digits in the key value. So it is possible to take approaches to sorting that do not involve direct key comparisons. Of course, radix sort in the end does not provide a more efficient sorting algorithm than comparison-based sorting. Thus, empirical experience suggests that comparison-based sorting is a good approach. Radix sort relies on comparison as well, and so can be modeled by the technique used in this section. The proof that any comparison sort requires uh, omega and log n comparisons in the worst case is structured as follows. First, comparison-based decisions can be modeled as branches in a tree. This means that any sorting algorithm based on comparisons between records can be viewed as a binary tree whose nodes correspond to comparisons, whose branches correspond to the possible outcomes. Next, the minimum number of leaves in a resulting tree shown to be factorial of n. Finally, the depth of the tree with n factorial leaves is shown to be uh, omega n log n. The proof of an omega n log n lower bound for sorting relies on the concept of a decision tree. Decision tree is a binary tree that can model the processing for any algorithm that makes binary decisions. Each binary decision is represented by a branch in the tree for the purposes of modeling sorting algorithm. We count all comparisons of key values as decision. If two keys are compared, the first is less than the second, then this is modeled as the left branch in the decision tree. In the case where the left value is greater than the second, the algorithm takes the right branch. Here is a visualization that listed decision trees and the sorting lower bound proof. XYZ. First step in insertion sort is to compare the second element y with the first element x. Yes, no. The third element z is compared to the second element in x. Yes, no. And then z and y are compared. Oh, this is the decision tree. Oh, that's why we'll take n log n time. In a perfect tree, it will have n factor, no, 2 to the power of something, right? Tree with n nodes require a minimum of log n levels. Because there are at least n factorial nodes in the tree, we know that the tree must have log n factorial levels. Accordingly, the decision tree for any comparison-based sorting algorithm must have at least one node that is omega n log n levels deep. The deepest node represents the algorithm's worst case. In the worst case, any such sorting algorithm must require n log n comparisons. Any sorting algorithm requiring n log n comparisons in the worst case requires omega n log n running time in the worst case. Because any sorting algorithm requires omega n log n running time, the problem of sorting algorithm also requires omega n log n time. You already know of sorting algorithms with O n log n running time, so we can conclude that the problem of sorting requires theta n log n time. As a corollary, we know that no comparison-based sorting algorithm can improve on existing theta n log n time sorting algorithms by more than a constant factor. Which of the following is not relevant to the sorting problem lower bound proof? If a bubble sort this, then if the upper and lower bound for a problem meet, then understand the runtime constant. Proved the lower bound for the sorting problem is omega n log n technically only applies to comparison-based sort. This means we can find other approaches such as radix sort to solve the problem faster. False. Lower bound for a problem is defined to be the maximum cost, well, the minimum, right? Cost of the best case input, no. Best possible cost for any algorithm. Upper bound, cost of the worst case that we know for the problem. The upper bound, cost of the best algorithm we know for a problem. Yeah. The upper bound for a problem is defined to be, wait, I've already seen this. Okay, it's the same question. Yeah, this seems to be the summary. So I will end the stream here. I've been streaming for like an hour and 40 minutes. And then I think I will skip this chapter. It's not about data structures, it's more about memory management. I will skip this. I'll come back to it. I will read about indexing, generate trees, graphs, and advanced data structures, and then I will come back to this chapter, file processing, hashing, and memory management. I'll come back to them later after I finish with the lower four chapters. Anyways, I will end the stream here, and yeah, I will see you guys next time. Bye.